is the International IAQA certificate for GCSE biology, and we're going to consider the surface area to volume ratio concept. We've been thinking about adaptations of organisms, and one of the key adaptations of heat retention or water loss is the discussion of the surface area to volume ratio. So we're just going to spend a little bit of time making sure we understand exactly what that means and how to go about explaining it. We've spent some time considering organisms such as polar bears and describing that they are really well suited to live in cold conditions because of their small surface area to volume ratio. Conversely, we've looked at plants that live in jungle rainforest areas, and we described them as having a very large surface area for their volume ratio. What we haven't talked about is what that actually means. It's simpler to think about, rather than think about an individual organism and its size, let's think about it as a cube instead. So we could perhaps consider that a cube with length side 1 centimetre, 1 by 1 by 1, as being a small organism such as a mouse. And that's, if we look at this line, this row of the table here, if we were to measure the surface area, total surface area of the cube, so the surface area of one side, multiply that by the 6 sides that a cube has got, we'll get a surface area of 6. Okay, so it's 1 by 1 on each side, gives it a 1, and then 6 sides makes it 6. Whereas if we measure the volume of that, just the volume alone, it's 1 by 1 by 1, which again turns out to be 1 centimetres cubed. That's squared. But what we're interested in is the ratio between the two. How much surface area is there available for molecules to move out to the outside world from inside? So, for example, water inside the organism being lost, or heat being lost. How much surface area is available relative to the amount of space inside? And to do that, we look at the surface area to volume ratio. So therefore, surface area to volume ratio, we write the surface area first, 6, volume 1, 6 to 1. But we need a single figure, so we divide one by the other to give a total of 6. A single value. Now if we consider a much bigger organism, for example a bear, we could represent that by a much bigger cube. And this cube, for example, let's just call it this row here, of side length 3. This one might be 3 centimetres all the way across here, by 3 centimetres, by 3 centimetres. So again, the total surface area of one side is 3 times 3. 6 sides, multiply that by 6, gives you a total surface area of 54 centimetres squared in this case. To consider the volume, 3 times 3 times 3 gives you 27. So if we were writing that in its simplest form, we would say the surface area to volume ratio was 54 to 27. If we cancel that down to its simplest form, we will get 2 to 1. In a single figure, 2 divided by 1 gives you 2. So, although the organism's total surface area has gone up as the organism got bigger, which is what you expect, total surface area of a mouse is clearly much smaller than the total surface area of a bear. So the surface area increases with size, as does the volume. Again, the total volume of a bear is far greater than that of a mouse. But the proportional ratio between the two, surface area to volume ratio, has actually decreased has the size of the organism increased? So this you can consider your size of organism. And here is your surface area to volume ratio. So as the organism gets bigger, the surface area to volume ratio gets smaller. So in real terms, what that means is that there's much more space inside of a cell, an organism, that is larger relative to the amount of space there is available on its surface for exchange and therefore loss of things like heat and water. And that's a crucial concept, not just for adaptations, but for an awful lot of biology. We might apply the same principle to adaptations of the gut or the lungs for exchange and uptake of food or oxygen, and all those sorts of places wherever surface area and exchange and rate of movement of molecules is required. So this is a key concept to apply across your biology, but is particularly crucial in explaining why organisms are adapted to their particular environment.